Okay, welcome everybody. We'll start our session off with a karakia. So if you all say it along with me. Whakataka te hau ki te uru. Whakataka te hau ki te tonga. Kia mā kina kina ki uta. Kia mā taratara ki tai. Ehi ake ana te atakura. He tio, he huka, he hauhunga, haumie, huie, taiki. So for the benefit of our wider audience, a karakia is a prayer generally used to ensure a favorable outcome of events and undertakings such as this one. Welcome to our session, which we are holding in celebration of the International Day of Women in Statistics and Data Science. You'll hear from a number of women who work in the statistics and data science space in Aotearoa, New Zealand. As it so happens, all speakers today have a research focus in biostatistics. So we are by no means representative of all the women statisticians and data scientists in New Zealand. This session is sponsored by the Biostats Centre at University of Otago and the New Zealand Statistics Association. The speakers you'll hear from today represent two of the 8 universities in New Zealand. One is the University of Otago, which has campuses in Dunedin on the South Island and Wellington on the North Island. The other university is Victoria University of Wellington, which has several campuses in Wellington. Before we get to the presentations, we'll briefly introduce ourselves. My name is Nokta Baswanda, and I'm a senior lecturer in statistics at the School of Mathematics and Statistics at Victoria University of Wellington. I am also the secretary for the New Zealand Statistical Association, and it's my pleasure to be here representing the NZSA. So we'll now stop screen sharing to allow my colleagues to introduce themselves.
Hi, I'm Claire Cameron. I'm a member of the Biostatistics Centre at the University of Otago in Dunedin.
Over to you, Gabrielle.
Kia ora, I'm Gabrielle Davey. I'm a Research Associate Professor in the Department of Preventive and Social Medicine at the University of Otago.
And Ella.
Hi, I'm Ella Yosua. I am a Senior Research Fellow or Biostatistician in the Biostatistics Centre in Otago.
And Alice.
Kia ora, I'm Alice Kim. I'm a biostatistician at University of Otago, Wellington.
Also, Jill Hazard is going to be presenting a section in this series, and she's just not able to be here today, but she's a member of the Biostatistics Centre at the University of Otago also.
All right, we'll now go back to the, continue with the introduction. So I'll talk about the NZSA first, and then I'll hand over to Claire to talk about the Biostats Centre. Okay, so the NZSA was founded in 1984, so it's been going for about 38 years now. It's the only association for professional statisticians in New Zealand, and has close ties with other statistical associations around the world, in particular the Statistical Society in Australia. Our main activities include an annual conference that the other universities around New Zealand take turns to organize. We also have input into high school curriculum through a very active education subcommittee, and that includes some school teachers as members. Earlier this year, we started a mentoring program where an early career statistician is matched or paired with a more experienced one as a mentor. And through that, there's an exchange of knowledge and the mentorship goes on. We also have a very active early career and student statistician network that organizes their own events. For example, later this year, they'll be holding a mini conference jointly with the Statistical Society of Australia. Okay, I will now hand over to the Biostats Center so that they present about what they do before we move on to our sessions.
Sorry. Hi everybody, as before I said, I am Ella Yosua. I'm going to talk to you about the centre and the Biostats Centre in Dunedin, where first of all I'm going to start by providing some context about our beautiful country New Zealand, or Aotearoa New Zealand. This is where we are in the world. We are an island country consisting of two main landscapes, which is the North Island and the South Island. We are situated in the expanse of the beautiful Pacific Ocean, and although we sometimes get left off the world map, New Zealand is a popular tourist destination and it's known for our awesome landscapes, basically. So we're a really pretty country. Have a closer look at New Zealand. We're not very big. There's only about 5 million people that live in New Zealand, including the people that are presenting today. There's a move, so we're generally known as New Zealand in the past, or have been known as New Zealand in the past, but there is a move towards using our Indigenous Māori name, so hopefully we are going to move towards it being more official and being Aotearoa New Zealand. A lot of us talking today, or some of us, are from Dunedin, which is down the South Island. We've only got a population of about 130,000, and then the others of us talking live in Wellington, which is the capital city of New Zealand, and it's where our government convenes, and it's got a population of around 400,000 people, so it's much bigger than Dunedin. I think Wellington is the second biggest city in New Zealand. So the Biostatistics Centre is in the Dunedin campus of the University of Otago. The university is really old. It was founded in 1869, so it's about 153 years old, and it's New Zealand's largest university. There are 6 biostatisticians in the Biostats Centre. 4 of us are presenting. No, 3, because our director, Professor Robin Turner, she's unfortunately sick and unwell, so she can't make it. So there'll be 3 of us presenting today. The group was formed at the end of 2017. Although we had biostatisticians before in the Health Sciences Division, it was formally brought together all the divisionally funded biostatisticians. And in the division, there are also about another dozen who work in this area as well. And we form a very collegial group, and we often meet and have professional chats. So here in this picture is the clock tower, which is something Otago University is well known for, and it's a very popular view you'll see on the internet, and also most people have photos of their graduation photos outside this building. This is just another picture. Otago University has some really picturesque places, also very old. Some of the buildings, obviously we have nice modern buildings, but part of the attraction of Otago University is, I think, some of the nice classic buildings we have. So what do we do? As biostatisticians, we are academic staff who specialise in the application of statistical methods to health-related problems. And our main focus will be on collaboration. We would probably prioritise this. What we like to project to is also that we do not run a service. We are academic staff. So we advise on study design, which is really important. We collaborate with researchers. We read and advise on grant applications. We help formulate research questions, write about methods, advise on reporting of results, clean data, which is not fun, as you all know, sometimes, or we'll tell the people to clean the data for themselves. So we'll tell them how we want it. We'll advise on data collection, advise on data management, advise on and conduct analyses. So generally we help answer questions from researchers working on any health related problems. Some of these are one-off queries, but some of them are long-term collaborations. Not maybe speaking for everybody else, but my preference is for collaborations. We like to promote people being involved, like ourselves being involved in research as early as possible, as our expertise is actually relevant to the whole research process rather than just the analysis of data. So that's what we do. Thank you for your time. And now we will start our session 1.
Hello, everybody. I'm a Research Associate Professor in the Biostatistics Centre at the University of Otago. My talk, I've called it Statistics to Biostatistics, which could be one of the hardest titles to say or even to spell. And I just wanted to talk a bit about my career and what I think my contribution to statistics has been, as well as show you a little bit of the city that I live in, which is Dunedin, also known as Otapoti. So I grew up in Dunedin and I live here. This is quite unusual for a university person, I've discovered. I walk to and from work each day. Dunedin is very hilly, and so the walk home is a lot more of a commitment than the walk in. At the risk of being accused of parochialism, throughout the talk I'll include some photos of my walk so you can see a little bit of Dunedin. This is my suburb, Opaho. I belong to the Caucus of Women in Statistics, and to be honest, I wasn't aware of this group until a couple of years ago, and I'm now the New Zealand rep for that group. And the older I get, the more important I think these days and these organisations that are committed to or dedicated to women are. I believe in the strength of networks of women, which is why I'm happy to be a member of the caucus. And the caucus has already shown great support for me and my colleagues, so I really appreciate that. I think the reality, just to be negative momentarily, is that sexism still exists, and I've had many instances of my life of being seen as less credible than an equally qualified man, whether it's conscious or not. So I think it's a great opportunity for us all to build each other up. I studied maths at university because I was good at maths at school, and I had no real idea of where that would lead. I think as a young person, I believed that doing things that I found easy was slack, and doing things that I found hard was more worthy. I don't know why I was like that. I found statistics quite hard because there's a lot of grey in statistics. It's not all black and white. I did an honours degree in maths and stats that I finished in 1989. There's still a lot of grey in statistics. This is a path off Evan Street on my way to work. I bumped into one of my aunties in the street one day, and she said incredulously, "You could have done anything, and yet you chose maths." I did a master's in statistics in 1994. It was called Modelling Survival of Hector's Dolphins around Banks Peninsula, New Zealand. So this is on the left here is a picture of a mother and child Hector's dolphin. The study was a photographic study using natural markings to identify individuals, and they were interested in learning what the effect of the marine mammal sanctuary around Banks Peninsula was on this species, which is endemic to New Zealand. I did a dip grad in psychology in 1998, and I graduated with a PhD in statistics in 2009, and that PhD was called Open Population Capture Recapture Models and Diabetes in Otago. So this project was really my first step into biostatistics, which I feel is my statistical home. On the right here is the iconic University of Otago building that Alice spoke of earlier. Everyone wants their photo taken in front of this great building of ours. So I first worked as a mathematical statistician in 1990. I think that's the most impressive job title I've ever had. So I worked in official statistics at the Government Department of Statistics, as it was known back then. I've also worked as in the hospital as an information officer, and I worked in a teaching role involving first and second year stats teaching for many years. Prior to being in biostatistics, I also worked in ecological environmental applications. I did some teaching in zoology and was a consultant for zoology students for a while. So all of that stuff covered about 20 years. I started the best job ever in 2011 as a biostatistician at the University of Otago. It's turned out that biostats can be a very political topic because most people need biostatistical skills to do health research. I learned in this role to manage conflicts and unmet expectations. This is a picture of the entrance into the Dunedin Botanic Gardens, which is about the same age as the university, 150 years old. One of the things I love about what I do is that I collaborate with a wide range of academics and clinicians. My area of interest is the application of stats methods to health-related problems. So there's a huge variety in my work. No one really uses mark recapture models in health research, or no one that I've worked with, certainly, so I don't do that stuff anymore after spending quite a long time doing it. So I have done model selection, risk prediction models, mixed models, regression methods, sample design, survival analysis, meta-analysis, randomized controlled trials, online surveys. And I've also looked at scales and agreement, which are a real thing in biostats. I don't know everything about statistics, and it would be really helpful if I did. This is a picture of the duck pond in the Botanic Gardens, and on the right there is the band rotunda. So I've worked in a wide range of projects, tobacco retailing, older drivers, Legionnaire's disease, dietary sodium intake, oral health, pain management. I've done some research into graduate research, so PhD students. I've also supervised a few students, and I'm involved in the mentoring program that Noktava mentioned earlier. I really love that sort of stuff. I've had more than 50 publications so far. One of the things that I'm really happy about is that we were asked to write some primers for the New Zealand Medical Students Journal. So Robin Turner, Professor Robin Turner, our director, and Ari Samaraika, who is one of my colleagues, we've written 8 of these articles. They cover Kaplan-Meier plots, receiver operating characteristic curves, parametric versus non-parametric methods, sample size calculation in health research, statistical software choices, and 3 other ones that I actually led. Medical students in New Zealand do not have much of an opportunity to learn about statistics. So these primers are designed to be accessible to lay people, and they've proven to be quite good teaching tools as well. This is the herb garden at the Botanic Gardens. So the first one that I wrote, I suppose, was about p-values. So of course there's this worldwide issue relating to the overuse and misunderstanding of p-values. So we wrote this paper referring closely to the ASA statement on p-values that was published in 2016. P-values in health research are everywhere, and very few people understand them. If medical people are to engage in lifelong learning and have research-informed best practice, they really need to have a basic understanding of p-values in an attempt to sort the wheat from the chaff in terms of research. So we felt this was an important topic to cover. This is a bridge leading out of the gardens into the heart of the student area in Dunedin. The second one I wrote was about confidence intervals, which seemed like an obvious next step from p-values because they're generally a better way to present statistical results, you know, in many cases, and certainly in randomized controlled trials and the consort statement, they recommend the reporting of effect sizes and confidence intervals. So we just wanted to talk in some more detail about that. this is the park in front of the museum reserve, which means that we're getting close to my office actually. The last one is one that we've just written, and it's in press at the moment. So we talked about, well, we talked to medical students as if they may be either reviewers of journal articles or writing journal articles themselves, and to talk through the different parts of the paper, the abstract, introduction, methods, and that was in a bit more detail, results and discussion, and talk about what a statistical reviewer might be looking for. It ended up being quite a long article because it's quite a thorny topic, that one. So very recently, I got sent an email by a clinician or a student who was despairing of her project and not finding any introductory material in statistics that she could understand. So she wrote this great email, and I have to read it out because it's so great. I'm writing to you flushed with the excitement of reading your Biostatistics Primer series in the New Zealand Medical Student Journal. And she went on to say how thrilled she was to find them. And it makes me feel as if these articles are reaching the audience that we intended them to reach. They're pitched at the right level, and they're good for the subject of statistics. As she also said, the more I read now, the more I realize I don't know, which when you work in biostats, that's quite a useful thing for students and clinicians to recognize. So very happy with that. And this is the picture that we saw earlier. I just thought it was a really nice picture. And this is actually a magnolia tree that's in the old quadrangle, I think it's called, for the University of Otago. And every year someone in one of these buildings takes note of when the first blossoms appear, which is usually in August sometime. What do I love about statistics? Statistics has allowed me to follow this path into biostatistics, and I love biostats. I really enjoy the work that I do. Biostatistics, despite what some statisticians might think, is so much more than just statistics. You really need to be on top of health research and study design and many things in addition to statistics to be a good biostatistician. So it's been a great opportunity for me. And this is, oh, I should say that this is just one of the paths on my way into work. And this is as I go into the Botanic Gardens. Thank you very much. So does anyone have any questions they'd like to ask about that?
I have one, Claire. You talked in your slides about in your position, you've managed some conflict.
Oh, yes.
Yes. So what sort of conflicts have you had to manage, and how have you worked your way through those?
Well, the main conflicts that we have managed as a group is the sense that some people have that we're running a service. And so the conflicts arise from people wanting to engage us as if we're research assistants, or, you know, not treating us as collaborators. And you can put up with that for a certain amount of time, and then it gets very frustrating and you really have to say something. So, and also management expecting that that's what our role is. So we had a period of time where people were expecting that we would just be consultants, which has now become a bit of a dirty word in our group. So we had to do a lot of negotiating around that. I could talk for a lifetime about that particular problem. Does anyone else have anything to say about that? Like it's been very political because people need our expertise, and they'll do things like put our name on a grant because it might increase their chances of getting a grant, and then not actually involve us in the project. That kind of carry on, which isn't acceptable.
No, thanks, Claire. That's I think that's something that a lot of statisticians go through when because you're asked to help, and quite often, that's all you're regarded as. It's not as if people don't view you as having your own research interests and your own research portfolio.
Yes.
So it's quite
very frustrating.
Can be.
Do you think that's improving over time though?
I think it is because we were just a group of individuals, and we're now in the centre, and we can sort of draw in other biostatisticians to support and advocate for them if they need it. And we sort of have more of a profile now than we did a few years ago. So yes, I think it is improving. Yep.
I have another question, not in line with that, totally different. I don't know if you mentioned it, Claire, but because you had your education, it seemed to be maths and stats quite based. Did you even know that there was a biostatistician? Did you know that was an existing job?
No, I didn't really, because in maths and stats at Otago, maths and stats is very much, if they're into applications, it's mainly ecological, environmental, animal kind of applications, fisheries. So you'd know a lot of people that would move into those areas. And we knew about the biostatisticians. So there was Sheila Williams and Peter Herbison over here, but I don't know, it was never presented as a possible career path. No, it was, and I think that when you're in a stats group, they tend to see biostats as kind of an easy option, because they don't really see that you have a whole lot of complementary skills required when you're a biostatistician compared to being a pure statistician. So no, I didn't know about it. I'm very pleased that I came into it though.
Can I just ask a quick question? Do you have any suggestions or recommendations for early career researchers in biostatistics and statistics?
Oh my, well, I guess I remember when I was young, people said no one plans to be a statistician. Like no one goes to university planning to be a statistician. I do think, in my experience, there's a lot of, I think, I'm fundamentally not a girls' night out, women getting all together kind of a person, but I do believe that in maths and stats, it can be very blokey. So if I was at the beginning again, I would say get a mentor, and I would say form your own network of supporters, whoever they are. I think that's what I have tended to do, and that's what's really provided me with a lot of the strength that I've needed over the years to get to where I am now. I don't know if that's a helpful thing to say. I would have needed to have thought about that question.
No, thank you. That's very helpful.
Cool.
As an early career researcher too in this area, I'd say, yeah, the same kind of thing. Have people that you can ask questions and that you don't feel embarrassed to ask questions, because I think that's
because I think that you can run the risk of being quite isolated as a statistician.
And it's nice to ask questions. I think people get nervous about asking questions because it doesn't look good. But
I think it's normal. I think it's a normal way of growing in that subject, is to talk to others about your work. And
seriously, part of our job is just being question masters. That's what we do. We ask bazillions of questions.
Yeah. Well, I think that's probably more than my time. I can't see if you're recording.
Sorry, we're recording.
Hi, my name is Jill Hazard, and I'm a biostatistician here at the Biostatistics Centre at the University of Otago in Dunedin, New Zealand. So as for many biostatisticians, my pathway to becoming a biostatistician was not straightforward. Here is my CV of sorts. I began with a bachelor's and master's in maths and physics. Then after a break, when I had my children, I returned to university to do a bachelor's degree in human nutrition, followed by a PhD. As you may be aware, nutrition is a highly quantitative discipline, so they're desperate for appropriately qualified biostatisticians in their field. This led me to completing a postgraduate diploma in biostatistics. Over the last 10 years or so, I've been employed as a biostatistician in various departments at the University of Otago, but I'm now very happy to be a permanent full-time position in the Biostatistics Centre, where I can collaborate freely with health researchers from a variety of disciplines. So what do I love about statistics? Well, I guess I don't really think of myself as a statistician per se, but statistics underpins all aspects of my work as a biostatistician. The statistical analysis will inform the planning of the project and the study design. The statistical analysis will inform the preparation and cleaning of the data after it has been collected. The statistical analysis will then inform how the data are processed to make them suitable for analysis. And finally, the statistical analysis will be undertaken in order to answer the research question. I love biostatistics. I love solving problems and contributing to important health research. Along the side here, you can see some of the logos from some of the studies that I've been involved in. I also love training new health researchers as a co-supervisor of numerous PhD students. As biostatistics is one of the foundations of health science, I think it's important for health researchers to be appropriately supervised by a biostatistician when doing their PhD, not only to develop a few biostatistical skills, but also to develop a respect for biostatistics as a distinct discipline and not just something you can pick up by knowing a bit of code or by attending a short course. So today I'm going to share a brief example of the type of work I can be involved in by discussing learning effects in crossover trials. Crossover trials are really very elegant. Each participant undergoes more than one intervention in a random order. The effect of one intervention compared to another is then measured for each individual, so that each participant acts as their own control. This reduces confounding and more accurately estimates the effect of the intervention on participants. Because of the within-person comparison, the design is very efficient, so sample sizes can be quite a lot smaller than what would be required for a parallel trial, which can be very appealing for researchers. This is a nice example of a crossover trial that was carried out in our nutrition department quite a few years ago. Here, the researchers randomized participants to consume either a diet with butter or a diet with margarine for 6 weeks. They took bloods before and after the intervention to measure lipids. After this first 6-week intervention, there was a 5-week washout period where participants went back to their usual diets. Then they were put on the other diet for 6 weeks. Bloods were taken before and after the second dietary intervention too. With only 49 participants, the researchers were able to show that cholesterol levels were higher when consuming a diet with butter compared to a diet with margarine. A very nice experimental design with clear, unambiguous results. However, while crossover designs are fun and efficient, they're not always appropriate. Both your population and your outcome need to be relatively stable because of the repeated measures that are taken in a crossover study. Involvement in the study is often more intense for participants and can take a longer period of time. You have to look out for carryover effects. This is when the effect of one intervention is carried over to the next intervention. And you also have to be aware of potential period effects. This is when the effect of an intervention can be dependent on whether it is the first intervention period or the second intervention period. Over the last 5 years, I've had over 15 publications reporting outcomes from crossover trials. And while I have never come across carryover effects in my trials, I have kept coming across something that didn't feature in all the papers I read about how to do crossover trials properly. And these were learning effects. Learning effects are commonly understood. Someone gets better at a task as they repeat it. However, I'd never seen it explicitly discussed as an issue for crossover trials. Because of this, we decided that we would make learning effects a central feature of the primary outcome paper of our DREAM study. The DREAM study looked to determine whether mild sleep deprivation in children was related to eating in the absence of hunger. Not only did we get this published in the top nutrition journal, but we also had an editorial written about it where the author said, "The lessons learned from this study will be valuable for future research, and I sincerely thank the authors for sharing their experience with the scientific community," which was nice. Learning effects influence the assessment of the outcome measure. The outcome may not have changed, but the participants' response to the assessment of the outcome may have changed. Learning effects are a type of period effect in that the second intervention period is different to the first, regardless of the treatment. I've come across learning effects in some of the other crossover trials I've been involved in. When we subjectively assessed appetite in one study, we saw that participants responded differently on the second day of the study compared to the first. Because on the second day, the participants had learned when lunch would be served and what was for lunch, so they reported their appetite differently. Also, when assessing cognitive abilities in another study, we saw that all participants did better on the tests after the second intervention because they had learned how to sit those tests after the first intervention. The assessment of eating in the absence of hunger provides a very nice example of a learning effect. In the DREAM study, the children underwent a week of going to bed earlier or going to bed later to be able to compare them when they were mildly sleep deprived compared to not mildly sleep deprived. After each intervention week, they came into the clinic and were provided with lunch. They were allowed to eat as much as they liked and were encouraged to eat until they were full with their parent in the room. Then, after a small break, the child was taken into a room without the parent. There was a buffet of treat foods and they were allowed to eat as much as they liked. There were toys and games to play with if they didn't feel like eating. The food was weighed before and after, and the amount consumed represented their level of eating in the absence of hunger. However, kids are not stupid. The second time they came in to do the experiment, they ate less of the lunch course to save room for the treats, and then they ate more of the treat foods. They did this whether they were tired or not. Sleep deprivation had nothing to do with it. This meant that we were not able to answer our research objective because of those learning effects. So what did we do? We analysed just the first intervention period as a parallel trial. We were massively underpowered. We wasted all the data from the second intervention period, and we were not able to make firm conclusions. We were aware that there may be a potential learning effect, so we did tell the children at their first meal that there would be a dessert coming up. But seeing is believing, this did not remove the learning effect. Other ways to overcome the possibility of learning effects in your crossover trial is to run a familiarisation phase at baseline. You can change the primary outcome to something that can be assessed without learning effects, or just change the method of assessment of the primary outcome. Finally, it may be that a crossover trial is not appropriate and a parallel trial is a better option. So in conclusion, consider the possibility of learning effects when designing your crossover trial, and know that even if your study fails, you could still get it published in a top journal and be applauded by other scientists. And of course, always have a biostatistician on your team. I'd just like to finish by acknowledging my collaborators, the DREAM team, and in particular, Associate Professor Sheila Williams, who first taught me about crossover trials. Note that everyone I'm acknowledging here is female, and it really is a dream to work with them all. Thank you.
Thanks, Jill. Jill is a great colleague, but unfortunately hasn't been able to be here today, so that was a recording. So therefore, we can't ask her any questions.
Kia ora. I'm Gabrielle Davey from the University of Otago, and I'm going to talk today about riches from rags, so health research using routinely collected data. I've built a career in health research, largely involving the analysis of routinely collected data. In brief, my career pathway involved undergraduate training in mathematics and statistics. And at the start of my second year, a flatmate was showing me her textbook, which piqued my interest. And the next day I changed my course to include epidemiology with her. And that's really what set me off on this career pathway. In my fourth year, I chose an honours project with two supervisors, one statistician and one biostatistician, and was fortunate to be able to use data from the Dunedin study, arguably the most famous birth cohort study in the world. After a few years travelling, I was employed as a research assistant in the Clinical Epidemiology and Biostatistics unit in Melbourne, and from there undertook a master's in biostatistics. Next move was to work as a biostatistician in the University of Otago, Wellington, and then from there to Dunedin, which is where I still am. By routinely collected data, I mean administrative data sets that are often national data sets held by government agencies, such as hospital discharge data. These data sets are typically collected for a different purpose, with research being the secondary use of this data. Firstly, I'm going to present some examples of research projects where we've managed to get some research gold from administrative data. Following that, I'm going to provide some guidance on the use and analysis of routinely collected data in health research. As acknowledgements, I think it's important that we recognise data as taonga, which means treasure in Māori, the Indigenous language of New Zealand. Routinely collected data is taonga in that it represents individual person/patient records, and as such is considered to be associated with their life force. I also want to acknowledge those in the often large multidisciplinary teams I work with, as well as, and that's both those that I currently work with, but have also worked with during my career. This article, published in the American Journal of Public Health, is one of the first times that I analysed routinely collected data. In 1999, New Zealand lowered the minimum purchase age for alcohol from 20 years to 18 years. And using national traffic crash reports and hospital discharge data, we tested the hypothesis that this increased traffic crash injuries among 15 to 19-year-olds. Our results showed that significantly more alcohol-involved crashes occurred as a result of the 15 to 19-year-olds than would have occurred had the purchase age not been reduced to 18. This research has been used to petition the New Zealand government to consider reinstating the minimum purchase age to 20. And it's also been used internationally in informing the debate around purchase age/drinking age. The data for this publication on the trends and determinants of excess winter mortality in New Zealand, the data for this came from New Zealand's mortality collection. In this analysis, generalized negative binomial regression models were used to compare mortality rates between winter and the warmer months. during the time period, around 1,600 excess winter deaths occurred each year, with winter mortality rates 18% higher than expected from non-winter rates. This research formed part of a body of work on the role of housing and health. And there's a research program run out of Wellington, He Kāinga Oranga, that focuses on improving housing quality and health outcomes. And they've successfully lobbied for minimum insulation standards for housing in New Zealand, which has involved considerable retrofitting. And will also have, was shown in some research studies to have measurable health gain. Some considerations when using routinely collected data. As a starting point, have you thought about what data is routinely collected? As an example, have a think about a two-car collision in which one or more occupants is seriously injured. You can see here that that one event can generate a range of routinely collected data sets. Obviously not for the whole journey, but each data set collecting different aspects of the event. So we've got emergency medical services, ambulance or rescue helicopter. There'll be hospitalisation. If it's a serious event, data might be captured in the major trauma registry. New Zealand Transport Agency will also be involved and look at the aspects related to the crash in their crash analysis system. New Zealand's no fault injury compensation scheme, the ACC, will also be collecting data from this event. And if the crash was fatal, there'll also be data in the mortality collection and in coronial records. Now, this is not even a complete set. It may be that as part of your hospitalisation, there'll be pharmaceutical data that's involved as well, and yeah, a range of data from that event. Obviously, if different events will also, like cancer, will involve other routinely collected data sets. Just a heads up, in case you were wondering, even though it's routinely collected data, it still requires ethical approval to analyse. As to sources of administrative data, New Zealand's Ministry of Health has 14 national collections, and I'm sure that internationally governments have a range, especially ministries of health, have a range of data sets available for research purposes. We're also fortunate in New Zealand to have the integrated data infrastructure, which is a research platform that provides an opportunity to analyse administrative data that's been pre-linked from a range of government agencies and non-government organisations. It's really important when using routinely collected data to understand about where the data's come from and some of the caveats that might also go with that. Published papers and discussing with other researchers who have published using those data sources is also useful. It's really important with routinely collected data that you check your data quality. Accuracy is one dimension of data quality. This example shows that ICD-10 coding in a random sample of injury-related hospital discharges was a variable quality, depending on the degree of specificity of the ICD code required. The gold standard here was the Ministry of Health's Senior Advisor in Clinical Coding. And so we compared what was recorded in the hospital discharge data with what Mary Ellen, the Senior Advisor, coded. It's obviously useful to know when designing studies, selecting cases or categorizing cases that use ICD, which is the International Classification of Diseases codes. Data completeness is also important to consider. Sometimes fields are mandatory, but missing data is often an issue, especially with sensitive fields such as alcohol use, smoking, or BMI. This example shows the problem of missing BMI in UK primary care records. For those with incident type 2 diabetes, BMI was missing for 7%, whereas in the comparison group, 41% were missing BMI. It was thus essential to use multiple imputation before estimating the adjusted hazards ratios for fracture. I'm not going to go into these other dimensions of data quality, but they're just important to be aware of, and there's more details on the website. It's important to remember that routinely collected data aren't primarily collected for research purposes, and this is reflected in what they capture and in their data structure. So some are person level, like the mortality collection. Some provide data on a region or an event, for an example, meteorological data. And some are person event data, such as hospital discharge data. Although it depends what you mean by event, and it's important to consider. So this is an extract from our hospital discharge data dictionary that indicates that an event, that a discharge, that someone's stay in hospital can also have a new record generated for a statistical discharge, or if they're transferred to another healthcare facility. So as part of this process of using routinely collected data, we often have steps involved where we transform administrative data into analytical data. So we've undertaken this study with some collaborators, looking at sort of options in terms of that process. Is it best to identify injury hospital discharges before or after we exclude short stay ED events? So this is part of the process of what we do when we're transforming the hospital injury discharges into an analytical data set that involves hospitalized, non-short stay emergency department incident injuries. So the short stay ED events, the reason why we excluded those was it became obvious that different district health boards, so different areas in New Zealand, were including short stay ED events or submitting them to be included in the hospital discharge data set at different periods in time. We now have complete capture of all short stay ED events in New Zealand. So depending on what time period you're analysing, you may not need to exclude short stay ED events. But just another heads up that they are administrative data sets, and so thus can be affected by short stay, by changes in administrative practices. The breadth of research questions that can be addressed with administrative data increases considerably when multiple data sets are linked. So I'm currently involved in a project evaluating the impact of pre-hospital care on mortality following major trauma. And to answer the research questions, we've linked emergency medical services care data with the major trauma registry, and separately for those that didn't survive to hospital, we've got information from the mortality collection and from coronial records. Data linkage can be deterministic if we're fortunate in our hospital system to have national health identifiers, so person identifiers that can be used for deterministic linkage. But with other data sets, those NHIs are not available in coronial data, so that linkage had to be probabilistic. Depending on the research questions and the data obtained, denominators might be available in your analysis data set, but often the administrative data sets provide the numerators, and we need a different source for the population denominators in order to calculate rates. Statistics New Zealand is a great supplier of denominators for our research, and similarly, internationally, the government agency for statistics would be a fantastic source of denominator data. But the Ministry of Health may also be an appropriate denominator. In terms of the impact of different denominators, COVID vaccination rates are a really good example of the differences that you can get. So during the height of the pandemic, the New Zealand Herald had on their website the vaccine tracker, eligible population, 4.21 million. And as at November 2021, when I took this snapshot, 83.4% of the eligible population had been fully vaccinated. The 4.21 million is a Ministry of Health estimate from the health service user data set. So that denominator includes people enrolled with a primary health organisation or where the Ministry of Health had a record that they'd used health services. As you can see, there's another tab that was available on the New Zealand Herald website that gave the Statistics New Zealand denominator, which was estimated to be 4.36 million. And you can see that using that denominator, less, so 80.6% of New Zealand was considered to be fully vaccinated. So given that New Zealand was very focused on reaching a 90% target of fully vaccination, you can see that the use of the denominator does play a big role. So it's really important to understand the biases resulting from the different denominator choices. And this has been relevant for some work I've been involved with recently as part of a rural health project comparing vaccination rates between urban and rural residents. In conclusion, there are definitely riches and rags, but don't underestimate the time required to answer health research questions using administrative data. Don't let others fall into the trap that it'll be easy or quick because the data is already collected. To end my presentation and to bring it back to the theme for today, what I love about statistics and data science is that they're the tools that make it possible to answer research questions. They are crucial in providing the evidence to informing decision making. And I really enjoy collaborating in multidisciplinary teams, and that includes supervisory teams for students as well. So thank you. And I'll answer some questions now with the team, but I'm also open if anyone wants to, that's watching this, wants to send me an email as well with a question in it. Thanks.
Good thinking, Gabrielle. I didn't think of putting my email up there. I have a question.
Is it easy?
It probably will be easy. It might even make you laugh. So given that there's so many sources of routinely collected data, are you actually like the expert in all of these sources, or is there someone out there who's the grand poobah of routinely collected data that knows about everything? Or when you start on a project using routinely collected data, is it just a matter of seeing how you go?
That's a really good question. So I started, as you probably realized through the slides, doing a lot of my work in injury. And so that helped in terms of having a narrower scope in terms of becoming familiar with the data sets relevant for injury research. I definitely did liaise with other colleagues and experts at the Ministry of Health in terms of those routinely collected data. We're really fortunate to have a analytics team within the Ministry of Health that are really open to sort of forward and back in terms of either via email or in person in terms of, so do you capture anything along these lines? Or I've looked at the data dictionary and it looks like these are the things that I need to be asking you for. Is there anything else I'm missing? I guess once I've become familiar with sort of the cornerstone data sets, which for me have been the Ministry of Health's hospital discharge data and the mortality collection, I've found it's been relatively easy from there to move to other, either to tack on other data sets, say to then combine that with ACC data, where that's been more of an unknown, or also to move into other disciplines. So I'm currently working in sort of cancer disparity research. And because I'm familiar with the hospital discharge data structure and the mortality collection data structure, and obviously bringing it back to the multidisciplinary team, so working with people that are experts in cancer research, we can then combine our knowledge together.
Complicated. Sounds very complicated. And also accessing it will be complicated. But I guess the IDI sort of helps bring some things together. Sorry, I don't mean to hog the questions.
No, that's all good. Yeah, that integrated data infrastructure does make access easier in some senses, but it also has a large approval process, and there are a number of steps involved to getting access to the data in the IDI. Outside of that, say the Ministry of Health does provide personally, obviously with ethics and sort of research study approval, but does provide access to unencrypted data sets that are sort of de-identified, that they can provide to researchers.
Cool.
I have a question, Gabrielle. Thanks for your presentation. That was quite interesting. I've also come across issues with routinely collected data where, because it's an administrative data set, it's in most cases data sets are meant for administrative purposes, and that means there may not be the information you need to answer certain questions. So to what extent do you think that problem goes into shaping the research we can do or limiting the research we can do? I know it's a resource of information, but there are some questions that you can't answer.
Yeah, very true. Because it is routinely collected, there's no ability to add questions to it. Although some would argue differently a little bit, say with the census, I know that they open that up now and again for researchers to provide input in shaping. There's a limited scope with some of the questions that can be added to the census each year. But yeah, on the whole, you don't, and that's a very forward-looking approach. You are limited to the data that's there and to the quality of the data that's there as well. So with another project, we've been sort of feeding back some of the data quality issues that we've been observing in the hope that that will then improve data collection into the future. Yes, definitely not all research questions can be answered using routinely collected data, and I think but it might be a way to be able to maybe measure or estimate and describe a particular issue that then could be answered with a more purpose-built study in which you collect the data at the same time. Yeah, there are pros and cons, as we know, to any research study, and we'd like to think that it's likely going to require that the world isn't going to change on the basis of one research study, and that it's going to be sort of the body of evidence from possibly routinely collected data, purpose-built studies, maybe quantitative and qualitative research as well. That kind of, yeah, that helps answer the research question, or the research, the area, the body. Unknown.
Yeah. Thank you.